Today I'd like to talk to you about the Diels-Alder reaction. In this reaction, we have a 1,3-diene, also known as a diene, reacting with an alkene, also known as a dienophile, to form a cyclohexene product, also known as an adduct product. To show you guys the mechanism, the pi electrons between carbon 1 and 2 move in between carbon 2 and 3. The pi electrons between carbon 3 and 4 move out to form a sigma bond between carbons 4 and B. The pi electrons between carbon A and B move out to form a sigma bond between carbon 1 and carbon A. This reaction is a concerted reaction, which means all bonds are being broken and being formed at the same time. In this reaction, we have 2 sigma bonds being formed and 1 pi bond, and we're breaking 3 pi bonds. Sigma bonds are stronger than pi bonds, so the overall reaction is exothermic, and because of this fact, this sigma bond product, or 2 sigma bond products, it's a driving force to form the products. This reaction is important because we're building larger carbon frameworks from smaller organic starting materials. A major consideration of the Diels-Alder reaction is the conformation of the diene. Here we have 2 extreme conformations, the S-trans and the S-cis, represented here in equilibrium, with the diene more likely to be in the S-trans conformation. S here stands for single bond, and trans stands for the alkenes pointing in opposite directions. In the S-cis designation, S once again stands for single bond, and cis stands for the alkenes pointing in the same direction. The diene must be in the S-cis conformation because the proximity of the dienophile and the diene must be close enough in order for a reaction to take place. In conclusion, the Diels-Alder reaction is important for building larger carbon frameworks from smaller starting materials. This classic organic reaction was discovered by Kurt Alder and Otto Diels in 1928, and because of how important this reaction is to synthetic chemistry, they were awarded the Nobel Prize in Chemistry in 1950.